this recorder right now, in case you want to see the lecture. So first of all, yes, I will be grading your homework. Do not worry, you have to just not submit it or just intentionally made fun of yourself if you're going to pass, in the sense that if you did 3 of them correct and actually tried on the other, you're going to pass. So don't worry about the homework. It's just a matter of me going through them. I will write some comments, but if they're unclear, unsatisfactory, whatever, email me or just, talk to me about it. Okay. Other than that, we will have only one lecture, 1 hour tomorrow. That's what the poll suggested. Although only 20 votes, so I assume nobody cared, which is fine by me. But regardless, let's just start. So I'm going to do integrals, okay? Sad part, it assumes you're pretty good at derivatives. I don't know how many of you are, but just, if you're a little bit panicked or you can't follow me at some point, it's more or less because I'm going to employ derivatives, but I'll let you know. So just stop me if anything, okay? So we're going to do integrals. What? Oh, yeah. Yeah, we've been here. We're going to do integrals, as I said. Now, a little bit zoom out. Okay, cool. So what did you learn up to now? You learned that the derivative of x squared, derivative of x is 2x, all right? And you learned that this fancy, ugly formulation, or x squared, everything with a dot here, is equal to 2x, okay? And this is your derivative. Well, integrals are just exactly the opposite thing. So technically, integral of 2x is equal to x squared. Okay? This is the whole idea. Now, obviously, just like in all math stuff, we have an ugly notation for it. So, and that notation is integral of 2x dx is equal to x squared. Okay? It's just a notation. And now, if we want to be thorough, we got to add a constant. What's the whole idea? In derivatives, you're taking derivative of the left side in order to get the right side. In integrals, you're taking derivative of the right side to get the left side. Okay? It's just like the opposite operation of taking a derivative. That's the whole thing here. Now you understand why I said you kind of need derivatives for this. Anyway, I know this sounds like an extremely informal proof and just like an explanation, but this is genuinely the definition of an integral. So if you have, the definition is something like if f derivative of x is equal to f of x, small f of x, okay? This is for all x's, okay? Then you have that integral of f of x dx is equal to big F of x plus a constant. Okay, why is that constant? Because if you take a derivative of the right side, it doesn't matter. The constant just disappears. Okay, good. Okay, I'm out. This is it. This is integral. This is all you need to know. We're done for today. Kind of. Not really. Niels is gonna fire me, so I got to teach you more. Okay. Now, what do we do? I guess let's just take an example, right? Let's just take an example. Let's do x squared dx. So until you just look at it and you know it, which just is practice, the way you think about solving this is, what do I need to take a derivative of, okay, in order to get x squared? And it's a polynomial, so you probably think it has to be some x to the third stuff here, right? X to the third, when you take a derivative, it gives you x to the second. But when you take a derivative of x to the third, you get 3x squared. So it's not good. What about x to the third over 3? if I take a derivative of this, I'm just gonna get x squared. Okay? So this is just equal to x third over 3 plus a constant. Okay? And I know it looks really simple, and then you're gonna look at your seminar problems and you're gonna have no idea how to solve it, but it's just it just goes like this, you know, it's just progress. So you just gotta take it slow. But obviously there's a formula for this. This is just how you think about stuff. Like if you forget the formula, no worries. This is exactly how you look if you don't know the integral of a power function. The formula is, and I think it's here, I'll actually copy it from the book since I found out that most of you actually use the book, and I just found the book, so let's not see it. The book literally says, if a is not equal to -1, then integral x to the power of a dx is just equal to 1 a plus 1 x a plus 1 plus c. Again, why is this? If I take the derivative of the right side, I'm gonna get the left side. Okay? Test it out for my 2 case that I just got. So replace a with 2, and I just get 1 over 2 plus 1 x2 plus 1 plus c. So exactly what I got. Okay? And again, if you forget the formula, just no worries, it's going to be fine. Now, all I can do right now, literally all I can teach right now is more formulas of integration, which are just the inverse of your derivation formulas, okay? So I'm just gonna show you what these are, and then I'm gonna give you some like properties of how to compute integrals, and then we're gonna do one example and then definite. So that's kind of the schedule for the day, okay? I said here that a has to be different than -1. So it obviously means that the formula in case a is equal to -1 has to be different. So what is that? It's x to the -1. So that's 1 over x dx. Okay. And when you took a derivative of something and you got 1 over x, what was that? It was just log of x. Okay. Plus c. You got to be careful here. One little thing you got to be careful about is you cannot take log of a negative number. Okay, log of -4 does not exist. It has to be positive. So in order to correct that, this formula has an absolute value on x, guaranteeing it's positive. Okay. Now, other formulas, I'll just give you, I guess, the exponent formulas as well. So we have, let's say, I don't know. Let's just count them, I guess. So let's just put 1, 2, 3, the third one, and I'll actually copy it from the book because I believe in the book you kind of get everything you need to solve, probably even more. So let's just follow it. And Niels in his lectures actually uses them as well, but maybe like a different notation or something like that. Is there a question? Okay, just stop me if anything, guys. So integral e a of x dx. And I think I've already tortured more than half of you on this seminar with this derivative when we compute it. So yeah, in case you don't know, it's just 1 over a e a to the x plus c. Again, at this point, it seems like I'm just copying it, but it's literally not much more I can do than just go through the same logic. If you guys want, we can do it. What do I need? Like, this has to be equal to something taking derivative of. This is how you think. In case you forget the formula, it happens. I forget them all the time. So you got to find this thing that when you take a derivative, you get e(ax). And what I've told you about exponents is, unfortunately, they never go away through derivation. So 100% inside this parentheses, you have to have an e(a) to the x. Okay. You might even get it. Oops. You might even get a cheat sheet, I think, on the exam, but do not quote me on that, okay? It's still important to know how to get your own formulas and understand where they come from. At least, nobody's gonna ask you to prove them, but at least at a conceptual level, know how to compute them, okay? So again, exponents never get away, never go away for derivation. So I need something that taking derivative of is gonna give me e to the ax. So a normal choice, just to go out after it, is compute ea to the x derivative. And if you compute this, this is just a ea to the x, okay? And now, surprise, surprise, if I move dA on the other side, I got my answer, okay? If I move dA to the other side, which is a constant, I get that ea of x is equal to the derivative of eax over a. Okay, hence the result over here. Yeah. Okay. There's one more thing, which I think on the exponent, which I'm going to give you, and I think it's the only one that's a little bit more different. And then let's do some examples. But I think it's better to do some simple examples to start with. The other one was exponential, when you have a greater than 0 and a is not 1, because that would make a problem on the log. A to the x dx. Again, absolutely same logic. And again, in the lectures, I've actually tortured people with derivative of this. So, and if I have not, then it means I have not gone to your lecture yet, but I will. So no worries. To your seminar, I mean. Okay. And this is the formula again from the book. It makes sense why a has to be greater than 0 and why a cannot be 1, because otherwise you're going to have log of a negative number or log of 0 or log of 1, which is 0. So that's why those are 6's are. Okay. Now, just like derivatives, integrals are really, really nice to work with in the sense that if you have integrals of a f of x dx, okay, and this again, this dx just tells you which is your variable, because you might have you're probably going to get something like compute the integral of x to the m, okay, dx. Just this dx just shows you that, you know, m is the constant and x is the variable that you need to integrate over, okay? But if you have something like this, af of x, this is just equal to a integral f of x dx. So the constant jumps in front of the integral. You don't need to worry about that. And just like derivation, if you have integral f of x plus gx, so like a sum of it, you can just split it. Okay, you can just integrate each of them on its own. Okay, and I think it's enough theory for now. So let's just try like a simple example, see how it works. Okay, I'm technically in the lecture right now, so I'm going to be cheating and I'm going to do a simple example, but to still give you an idea of how things work. Okay, so yeah, this is all the theory on indefinite integrals. Okay, let's say I want to compute integral of x to the second plus 3x plus 2 d of x. Okay. Now, it makes it easier in the start to just split it across the simplest things you have. So this is just equal to integral x squared dx, integral 3x dx plus integral of 2 dx. Okay, and now we just solve them one by one. You can, yeah. You just solve them one by one. You can just compute them outside if you don't want to copy everything. So let's just take it, x squared dx. And now you can either use the formula, which was right here. You can use this formula right here. Okay. Or if you don't want to use the formula, then just think what's gonna be here. It should obviously be like an x squared and then over 3, right? Because when you take a derivative, it's a 3 pops down. So again, either the formula or your judgment, but it really is kind of simple once you know derivatives, okay? And I know it's bad of me to say once you know that stuff when you just learned it like a week ago, but yeah. I wanted to do derivatives, but I'll do integrals. Okay, now moving on. So I computed this thing. Now I'm going to compute this 3x dx. By the way, this c is just a constant, it doesn't matter. And I'll show you what I mean by it doesn't matter, in the sense that x plus x, the constant plus a constant still gives a constant. We don't care about it. It's just a matter of writing it out so that we know, or so that the grader knows what you're talking about, so that the grader knows that you understand this is an indefinite integral, right? Just like the L'Hopital case, where you have to write 0 over 0 whenever you're doing it. It's just a matter of notation it and dragging it afterwards, or you just so to be clear on what you're doing. Anyway, right here. So I have this integral. I have a constant that's free, so I'm just going to pull it out of the integral. Free integral x dx. And again, using the formula or whatever we want, this is just equal to 3. And okay, I can have a parentheses. It's x squared over 2. Because when I take this derivative, I'll get, x plus a constant. And what do I mean that we don't care about this constant? It means that this is equal to 3x squared over 2. And I know this is 3c, but it doesn't matter. You can just write plus c. Okay? It can be whatever. It's just like the family of functions that differ through a constant, but So now doing 2 dx, again, 2 jumps in front is a constant, so I have 2 integral of 1 dx, and what gives me a derivative of 1? Just x. So it's just 2 x plus a constant. So I mean just 2x plus a constant. Okay, so now coming back to my integral, I want to compute this x to the second plus 3x plus 2 dx. This is equal to, and I just add everything up. I have x to the third plus 3 and the constants again, but 1 at the end is enough. Plus 2 plus a constant plus 2x plus a constant. When you're adding all of these 3 constants, okay, note this can be constant 1, constant 2, constant 3. Like they don't have to be the same. Obviously, they don't have to be the same. They can be any constant in the world. They can be plus 2 minus a million or plus 1.5. It doesn't really matter what those constants are. It's just a matter of writing for now. Okay, so even if I have constant 1, constant 2, constant 3, I can just write this as being the x's, which are the actual important stuff, plus a constant, okay? All right. Yeah, so your only concern with these constants is when you have to compute an indefinite integral, which is just this type of integral that you see, just to write a c at the end, okay? This is the only thing you need to care about for now. Yeah, this is the indefinite integral. Any questions on it? Well, sure. Okay, now we're gonna go to what is called the definite integral. Obviously, if there's an indefinite, there has to be a definite as well. So now we're going to move to the definite integral. What does the definite integral mean? It means that you still have the symbol, but you have a and b, okay? And you still have the f of x dx. And it's still computed the exact same way. But the idea is that now, in your previous cases, when we computed the thing, right, we just had this formula of x and a constant. When you're having definite stuff, you're gonna get a number, like 2, like 5, I don't know, depends on the integral. Okay, that's kind of different. What is the, I said that the indefinite integral, the one before, is just basically the antiderivative, okay? And it's literally called antiderivative if you search in the book. The antiderivative of what's underneath the integral. In this case, the graph interpretation is something like this. Let's say this is your function, okay? This is my f of x. Integral can basically be, again, this is not formal talking, this is just for you to understand it, and technically it is true, but it requires a lot of analysis, so not go in detail. But this integral basically means add each f of x for all values from a to b. That's what it means underneath all these fancy notations, okay? So what am I doing? I'm just, let's say this is my a, this is my b, okay? And I'm just, and what's my value of f of x? It's here, okay? This is a value between. So the idea is I just add all these values, absolutely all of them, from a to b, okay? So if I technically kept going and I would just draw lines like this, like crazy, what would I get? I would just get the area under the graph. Okay, I would just get this area right here. I would just, it's like drawing, but I never drew color between the lines, so just pretend it's lining. Okay, the idea is that this definite integral just computes the area under the graph between a and b for function f. Okay, because it is summing over every value between a and b. Okay, like these lines basically are like, you can consider them as being a number of points, and I'm basically adding all of them up. Okay, literally everything that's under the graph I add up and I get a value. So the definite is just, you can consider it area under the graph of f of x between a and b. Okay. Questions here, if there are any. Okay, so now I'll hit you with a little bit of math stuff, in the sense that a little bit of analysis or whatever, but because it's in the book and in Niels's notes, using the intermediate value theorem. Does it actually help you when computing these integrals? Not really, but I have to write it, so I will write it right now. Did you have a question? No, okay, sorry for that. So the idea is that, as I said, I'm kind of adding over all of them, right? So this, in the intermediate value theorem, says that this f of x dx is equal to like a minus b multiplied by an f of c, where c is inside the interval a and b. Okay. Yeah. And now there's a whole discussion right here, which leads you to like solutions about why is this the derivative? As you probably know, or the definition of the derivative is, let's say, f prime is by definition the limit when h goes to 0, f prime of x, okay? When h, or I think in the book you have delta or delta. When delta goes to 0 of f of x plus delta minus f of x over delta, okay? And this is, and jumping from here, you can get why this integral. Well, let's compute it. This f derivative here, big F derivative is just small f, okay? By notation, it's f is f, let's say, is the anti-derivative of small f, which again, in parentheses means that when you take f derivative, you get f. Or when you integrate f, you get big F, okay? These are all like, they're exactly the same stuff. Yeah, if you replace that, you'll just get that. Let's apply the interval a minus b, and okay, yeah, let's do it. So I have f, and let's use c, okay? F of c is equal to this limit when delta goes to 0, f, big F of c plus delta minus f of c over delta, okay? And now let's just replace this delta with an a minus b, okay? Replace delta with an a minus b. If you don't really follow this or whatever, don't really panic. It's just like I've seen it in the notes, so I'm just putting it forward. It's more like showing you what the formula for this definite integral is, but don't worry, it has nothing to do with what I just told you. So yeah, I know it's kind of counterintuitive, but okay. So replace delta with a minus b, and I'll get f of c is equal to limit. I mean, I'll get up top f of c plus a minus b minus f of c over a minus b, okay? And now there's a trick that I can do with the exponents up, with the values up top, or in the limit theorem or whatever. But the basic thing that you're gonna get if you play with them, and I'll just write it out, is f of c a minus b, okay, is equal to, and I'll write it straight out, f of b minus f of a, okay? I know we jumped a little bit fast, but I don't really want to go into the specifics of playing with the derivatives, and it's again, it's just for you to kind of understand that this comes from the intermediate value theorem. But what was my f of c a minus b? This was integral from a to b f of x dx. So this is equal to f of b minus f of a. And this is the formula you're actually going to use. So this is actually what you need to memorize. When you're going to be solving stuff, this is what we're going to be using. And again, what is f? F is the antiderivative of f, of small f, which strong term means f derivative of x is equal to f of x for all x. Or, integral of small f of x dx is equal to f of x. Cool. So again, if you weren't a fan of the limit theorem, this is what you need. This is the formula we're gonna use. And so from now on, when you compute, when you're asked to compute, let's say, integral of ab f of x dx, it's literally just adding all the values of f of x from a to b in an extremely informal explanation for just to make sense for you guys. This is just going to be equal to, and here comes the notation, f of big X, and it's just the line between A and B. Okay. This is just a notation. This notation only means f of B minus f of A. Where again, f is, where f of x is just integral f of x dx. Okay. Now you know what this is. What this is as well. So what can I say? I can teach you some properties of this thing. Okay. So obviously, all the properties that you learned on the indefinite integral, in the sense like if you had a constant, you can jump out, or you can, if you have to integrate over some of things, you can just split them. Still applies here. Okay, they still work. But even you have now some like new properties, new things which you can use, and I'll show you. Let's say, what is integral from a to a of f of x dx? Well, intuitively, I'm adding stuff from 1 to 1, so I'm technically not adding anything, right? So it's intuitively 0. But if you don't believe me, then just let's apply the formula. Let's say I found this f of x. I have f of x from a to a. And it's just f of a minus f of a, which is just 0. Okay. So I know these are like maybe small properties or stuff that you're not really fond of or whatever, but they might come in play, and they just hopefully help you understand what you're dealing with. Okay. Now, what other stuff? What other things do I have here? I have if I have integral, let's say from -1 to 1 of an f of x dx. Okay. Again, think of it as addition. Just you don't write that down. Please don't write that down. Otherwise, it's gonna be bad. But just think of it. Okay. So I'm adding from -1 to 1. Can I just write this as from -1 to 0 f of x dx plus from 0 to 1 f of x dx? Yes, of course I can. I'm still adding the same stuff. I'm just splitting it into 2. Okay. What else? What else can I do? If let's say I'm integrating from a to b f of x dx. Okay. what is the value of like integral from b to a of f of x dx? Well, it's just it's just the inverse. You either believe me or you apply the formula. Okay, the formula tells you it's f of x between a and b. Okay, so it's f of b minus f of a. And this is the same thing, but only it's from b to a. So it's f of a minus f of b. Okay? So they're just opposite, okay? Yeah, these are, I guess, the only things that actually, properties that actually come to mind. Other than this, it's at this point from now on, you know how to solve integrals. There's not much everything I can teach you, the basic ones at least, okay? We're gonna learn, but maybe in the second hour, although I probably thought of doing some exercises, but we'll see. Exactly, because there are obviously, as math, there are some methods that you need to use in order to solve more complex. But for now on, for the time being, we can solve integral of, let's say, 1 over x dx from 4 to 8. I can do that, okay? First of all, what's the first step? When you have a definite integral and an indefinite integral, the first step is actually getting the antiderivative, primitive, definite integral, whatever you want to call it. They're more or less interchangeable. So I first need, whenever you're dealing with integral, I first need what if taken derivative gives me 1 over x. This should be the first question that goes through your mind when you're solving an integral. Okay. And you circle through your head if you didn't memorize the formula, and you realize it's log of x. Okay. It's log of x. And I know it's absolute value because it has to be positive. That's why I put it from 4 to 8, not to be stressed. But it's log of x. And now I told you that you need to carry a constant. And you're free to carry a constant. Okay? Because when you plug it in here, you get log of x plus c between 4 and 8. In this case, you are going over the same c, okay, for 4 and 8. Like when you're going to write log of 8 plus c minus log of 4 plus c. Oops. When we're going to write this c is the same in this case because it's the same function right now. I'm fixing the function and I'm going from between 4 and 8 at this point, okay? And it doesn't matter because the whole idea is this c goes away. It just disappears. When talking about definite integrals, there's no c, there's no constant. It goes away, okay? So my answer is just log of 8 minus log of 4. Yeah. Any questions? Otherwise, I think I'm going to do one more exercise. Let me see if I can find like a, let's say, a little more challenging one without being too challenging, if that makes sense. And then break, and we'll see what we do afterwards. But no questions right now? Okay, I mean, all the examples are pretty much what we have. Niels gives you an example of a function that cannot be calculated. You can find it in his notes. I would rather just do something that can be calculated. Again, one other property, I guess, that I didn't show you, but it can be applied, and it makes sense again. I mean, I gave it the example with -1, but I'll write it out in the format. Is if you have integral from, yeah, is it? Yeah, should be better now. My papers are on top of it. Okay, so if you have integral from a to b of f of x dx plus integral from b to c of f of x dx, this is just unsurprisingly equal from integral from a to c of f of x dx. Again, whole idea is if I'm adding from a to b and then from b to c, then it's the same as adding straightforward from a to c. Okay, it's the same. It's like the general of the -1 case I showed you before. This one. Okay, -1 because I can split over anything. This 0 of mine was just a random choice. I could have split over 0.5. Okay. Now, his other example was just let's compute integral from -2 to 3 of 4x to the third plus 6x dx. And again, he writes it straightforward. I would rather just do it step by step and slowly, this one, just so we know where we're at. And then, you know, if you can go speed through it and write the whole derivative up top, more than recommended. But I'm more of a basic kind of guy, so I just split it. So it's -2, 3, 4x to the third dx plus integral -2, 3, 6x dx. This 4 jumps in front, 6 jumps in front. So it's just equal to 4 integral from -2, 3, x to the third dx plus 6 integral -2, 3, x dx. And this is just equal to, okay, what is the antiderivative or what is big F of x to the third? It's x to the 4th over 4. So this thing is just equal to x to the 4th over 4 from -2 to 3. Okay? Close parentheses. Plus 6. What gives me x is just x squared over 2. -2, 3. Okay? So this is just equal to 4. And now I just replace my x with the values I have on the right. So it's 3 to the 4th over 4 minus -2, everything to the 4th over 4. Again, I said indefinite integrals, you don't care about the constant. There's no constant here, okay? No constant, I'm just getting a number. Plus 6, again, here I have 3 squared over 2 minus -2 squared over 2. And now I have not done this computation, but you know, I believe you can compute this in order to get what it is. It's just replacing the numbers. I don't have a calculator and it doesn't seem like he wrote it anyway. So yeah, it's just computation and everything here. But this is how we solve a definite integral. Any questions on how to solve a definite integral? And I know you're gonna go and be like, yeah, well, this really this makes sense, but what happens when we get a function? Yeah.
Could you explain again where the C disappears?
Yeah. So I said that integral that a definite integral from a to b of f of x is by definition f of b minus f of a. And it is f of x evaluated between a and b. And I said, okay, I did say that when you write it without a and b, when it's f of x dx, okay, do not forget about dx. It's equal to f of x plus c. This c can be whatever, okay? The idea is that when I plug in here, I have fixed my c. Like this function that I choose to integrate this f of x between a and b for c equals 5. Like it's fixed. It's a function in itself. Here, when I have this antiderivative, it's a family of functions. It's like for all c's, literally, all these family of functions, like for example, x squared plus any number, 1, x squared plus, 2 plus 3 plus whatever. If I take derivatives of this, I'm still going to get 2x. Okay? But when I integrate up top, I'm fixing a c. It's the same c. So let's just say I have f of x plus 12. F of x plus 12. Let's say the constant is 12 up top. Okay? And it's between a and b. This is how you have to think of it. When I replace, I'm going to get f of b plus 12 minus f of a plus the same 12. That's the whole idea. That's why I'm fixing that function when I'm going from a to b. I can't have like a different constant here. Okay? And in this case, I'll get f of b minus f of a alone. Okay, so this 12 goes away. The constant itself goes away in this case because it simplifies from a to b. And the only case in which it didn't simplify was in the case where, if I had a different constant here and here, but I showed you that's what I meant that we're fixing one. Okay? Sure, yeah. So indefinite, write it as a constant. Definite, the constant goes away, you can forget about it. You don't even need to write it. When you're solving it, you don't need to write there plus c minus c. Nobody cares about that. Okay? Don't write it in a definite. Yeah, cool. Well, I think it's a good time for a break right now. And then if you're bored with this, I guess we can just go to like methods of solving more complex stuff. Okay? Yeah, I'm sorry about that. Okay, yeah, so fast run up, I said that, okay, what you learned up to this point is that integral of small f of x dx is equal to big F of x if big small f of x is the derivative of big F of x, in which case big F of x is called indefinite integral or antiderivative or primitive, or there are multiple, everyone has their own saying almost. And then you learn about the definite integral, that it's basically saying, hey, find what the indefinite integral big F of x is and just subtract from f of b f of a. Okay, this is what you learn up to now, integrals. And we learned some properties, but now we're going to move on how to solve them. And we already saw the first one. It's the term by term, which is basically just splitting it until you know how to solve it. X2 to 3x, x to the power of 2 plus 3x dx. Maybe you don't know by heart what it is, so that's why you just split it into powers and then ... you compute it just like we did. Okay, this is called a term by term, pretty standard. Now we're gonna go to the integration by parts. What is integration by parts? Well, it all comes down to the product differentiation rule. Okay, and I think you learned it something like uv, everything derivative, is equal to u prime multiplied by v plus v prime multiplied by u. Correct? This was what you learned as the product rule in derivation. So why not throw an integral in it? What do I mean by that? Integral of uv prime. I mean, maybe there's a dx here because it depends on x, but doesn't matter for the time being. So let's just not put it. It's equal to integral of u prime v plus v prime of u. Okay? If the numbers themselves are equal, their integrals are equal. So what do I do with this thing? Great question. Well, let me first of all, let me make the u's and v's clearer. I think that's one step. Yeah, how about we choose different notation? Can I use the a and b because my u and v's kind of seem alike and I don't want it to be confusing. So let's just use x and y because my writing is really bad. So this is just equal to x prime multiplied by y plus y prime multiplied by x. Okay, same rule, same thing. And now throw an integral inside. X prime integral x prime y plus y prime x. Okay, now look at this. We don't know much about integration, but what do we know? What can we do here? Well, first of all, let's come back to the definition of it. What is the integral of xy, everything derivative? It is something that when taken derivative is equal to xy, everything derivative. What can it be? It's just xy, right? Again, the logic was the following. My claim is integral of xy, everything derivative, is equal, where x and y are just random functions, okay? Random functions. Is just equal to xy plus a constant. Okay? This is my claim. Why? Well, if I take a derivative of xy, I'm going to get xy derivative. So it makes sense, right? Yeah. No other way. Okay, now, what did I learn on the other side? It's x prime y. What is this integral on the other side? X prime y plus y prime x. Again, I don't know much I can do here. I know the term by term thing, so I just split it. Okay, so what is my end result? My end result is xy is equal to integral of x prime y plus integral of y prime x. X, y's are functions of some of a variable. I don't know, functions of a variable. Okay, and this is what it's called, what the chain rule is called. Okay, this is what integration by parts is. No worries, I will show you if there are any questions here. Otherwise, I want to show you like an example of what I mean by this. Okay. I don't know. Let's do it simple. So this type of integration is extremely applied when you have something of the type polynomial. Let's say polynomial of, I don't know what variable. Let's choose a multiplied by exponent of a. Okay. When you see something like this, you have to apply by parts to it because it gets out really nicely. Let me show you. Let me show you what I mean. Let's say we want to integrate a multiplied by EA dA. Okay, and notice I changed the x. I don't have dx. You can put anything there. It doesn't matter. This is like just hoping you get comfortable with stuff. Okay, what is this integral? Do I know this the derivative, the antiderivative of this by heart? It would be quite impressive if you did, because I don't know. Cool. So now I want to apply the by parts to it. Okay, so this is what I need to apply. I need to apply this thing here. And what is my train of thought? This thing cannot be this xy, right? Because I have an integral, so it has to be here somewhere. So I need to write these functions somehow. So let's say this is my x. Okay. And this is my y prime. Okay. Let's try it like this. Integral of a multiplied by e to the a, everything derivative. What is e to the power everything derivative? It's the same thing, okay? So d of a is equal to a e of a, no derivative. The derivative doesn't change there, so it's the same thing, okay? When you take a derivative of the exponential, it's the same thing. Derivative of e to the x dx is e to the x. That's what I'm using here. Okay? So these two are the same thing. Cool. Cool. Now, I'm going to use this form over here. Integral a EA prime dA. Okay? So I always look back to my formula. Always look back and see how I can use it. I have one term now that is a derivative. I know that if I add integral of derivative of a, EA untouched, dA. So if I take derivative of the other guy, I know this is going to be equal to a E of a. Okay? Just by using the formula up top. It's just like a product rule, literally just like a product rule. Okay? Okay. Let's go with it for now, and then I will, and then we'll take another example. Okay, now, if I compute, I get this integral e a prime dA plus what is the integral, what is the derivative of a with respect to a? 1 multiplied by e of a dA has to be equal to a e of a. Okay, and now, so my integral of a e prime dA is just equal to a e of a minus integral of e of a dA. Basically, same thing you had here, I just moved this to the other side with a minus. Okay, and you get this thing. Now, what is the integral of e to the power of a? What is the derivative of e to the power of a? It's the same thing. So my answer is a e to the ea minus e to the a plus a constant. No, don't forget about a constant. And this is my answer. Okay? Again, we'll do another example, but main idea comes from the product rule in differentiation. That's the main idea. So basically, if you have one of your terms derivative, you have to add the other term with the opposite derivative, okay? In order to get what's inside your integral with no derivative. Let's do something else. Let's come back to the x notation. Maybe that helps. So let's do, they're all of these type with ax, ex. Those are like the most famous applications, let's say, of this. But let's do this one as well. Let's do integral of x r multiplied by log of x dx. Okay? Another application. This is capital R, constant. I don't care about it. Cool. How do I look about it? I first try to see if I know the primitive, if I can find out the solution right from the start. And no, I cannot. I don't know it. Maybe Wolfram Alpha does. But now, what do you do? When you see a product inside, just try the chain rule. I don't know if it's going to work. I mean, this by parts differentiation integration. Just try it. I don't know if it's going to work, but 99% in this course is going to work. Otherwise, it's the third method, which we're going to study probably tomorrow. But 99.9%, this is going to work. So what do? You just take one of these terms. I'll take this one, the x to the r, and write its primitive or write its antiderivative. Okay. In my case, I know that x r plus 1 over r plus 1 derivative is equal to x r. Okay. So how about I just replace it? Just replace with this here. So my integral is equal to x r plus 1 over r plus 1 derivative multiplied by log of x dx. Everyone follow me on this, okay? I just replaced my xr with its antiderivative or with whatever. Yeah, yeah. Cool. Now, in order for me to apply the chain thing, I keep calling the chain thing, but the integration by parts thing, I need to add the term that keeps the first thing on without a derivative and takes a derivative of the second thing. Okay, so I'm going to add integral. The first term has no derivative next to it, no derivative, but I take a derivative of the second term. Okay, I take a derivative of this thing, dx. Okay, so I just switch the derivative to the other guy. And I know that this has to be equal to both of the things with no derivative. So this thing multiplied by this thing. Okay, any questions here? So this is how you do like integration by parts. Let's recap. What were my steps? I had this thing that I didn't know how to solve, but I know it's a product. So I thought, hey, let's use the differentiation by parts. Okay. In order to start differentiation by parts, you need a derivative. So I choose XR for the derivative because it's the easiest. Okay. And I noticed that XR plus 1 over R plus 1 derivative is equal to XR. Okay, so I just replace it in. Here I am. This thing becomes this term. They're the same exact term, but I just replaced that. Okay. And now I see this, and I'm like, okay, let's try and apply the integration by parts. So, in order for me to apply it, I have to add the same exact thing, but moving the differentiation sign to the other term. So I moved it to the other term, which is log of x. Now log of x is being differentiated. Okay? And this, I know by theorem that it is equal to both of the terms with no derivative next to them. Okay? This is just straight application of it. Okay? Cool. So what do I do now? Where did I go? This, remember, this is what I need to compute. This is what I need to compute. So this, again, copy it, nothing for me to do. I just copy it. This is just equal to, again, this thing minus this ugly thing right here, okay? So this is just equal to xr plus 1 over r plus 1 log of x minus, what do? I just move this on the other side with a minus. Nothing, I didn't, okay? Integral xr plus 1 r plus 1 log of x prime dx. Okay. And now we're going to ask me, okay, what do we solve? We got, so this is done. This is this part is done, right? There's no integral here. I'm done with this part. But what about this part? It looks extremely ugly. What did I solve here? Well, I have to take a derivative of log. So let's take a derivative of log and see what happens, okay? Again, my equation is integral xr plus 1 over r plus 1 prime, okay? Log of x dx is equal to just copy from your notes or my notes if you don't believe me, if you don't believe yourself or can't find, okay? And I have minus here of integral x r plus 1 over r plus 1. What is the derivative of log of x? It's just 1 over x dx. Okay? And I can simplify an x from here with the 1 from here. Okay? Because I have x r plus 1 up top and x down, so they just simplify diagonally. So I just get x r plus 1 or r plus 1 derivative log of x dx is equal to, again, copy this. Log of x minus integral x r plus 1 dx. Well, this doesn't look so bad. I know how to I know what the integral of a power thing is, right? I mean, I should know. You guys just learned. So now this thing, x r plus 1, log of x dx is just equal to r plus 1 over r plus 1 log of x minus, and what is that thing? It's, again, the 1 over r plus 1 pops in front, so it's 1 over r plus 1 multiplied by the integral of xr dx. And this is just, this integral is just xr plus 1 over r plus 1 plus a constant. Okay, and we're done. We're done because, again, this ugly thing is just xr. Okay. Any questions on this one? Do you guys want me to go again over what I did, how I got this, or let's do another example? Okay, so I'll go again, and then we'll do another example, and hopefully it's going to become clear. So, because I mean, I think as this is one of the main methods you're going to be doing integrals, if you don't, but it's gonna get better, so no worries. Okay, so I have to compute this integral of xr multiplied by log of x dx. Okay, I cannot separate these things, and I have no idea what the primitive is. So I think of applying by parts integration in this case. By parts integration says you have to have a derivative inside the integral. You have to have some derivative inside there. I don't have in my case. There's no derivative. I have xr multiplied by log of x dx, no derivative. So what do? I just create one by looking at the antiderivative of xr, okay? And I notice that if I take derivative of this thing, of xr plus 1 over r plus 1, if I take derivative of this, I get xr. Okay, I notice that this is happening. So I take this derivative and I replace it inside my function instead of xr. Cool. Now I have to compute this ugly thing. Does it make a difference? Not at this point, but I noticed I can apply integration by parts. What does it mean parts? You know, by parts, it means that I have to, that you can think of, you got to have derivative of each of the parts. I have, let's say, my first part and my second part. So I have here the term where the first derivative, where the first term is being taken derivative of. So I add the case where the second derivative, when the second term is taken derivative of. I copy the first and add the second, and the case where the second derivative is happening. Okay. And this has to be equal to both the things with no derivative next to them and no integral, which helps me solve it. Okay. After that, there's actually nothing happening. Nothing happening because, you know, once you get this, you just take a derivative of log, you get 1 over x, and then you know the whole story with power series. So I think I'll show you like some more examples of how to apply it rather than do the computation. So let me think. Again, all E of x's are great examples of how to use it. So let's try a little one with E of x. Let's have integral of x squared E of I don't know 3x dx. I'm asking you to compute this thing. Okay, what do? Well, again, you need a derivative in order to do by parts. And whenever you have E, the great choice of using derivative is E, because E does not change. That is a great choice. So I choose this term. You can choose the other one. You can try it. Like if you don't get it the first time, it's perfectly fine. It just comes with experience and loads of these exercises. But you just got to try it. So I'm going to try this E3x thing. Okay. I want to replace this with a derivative. Okay, that is what I want to do. So I'm just going to do exactly that. What is the antiderivative or indefinite integral of E3x? Is just E3x over 3. Okay. If I take a derivative of this, I will get E3x. Everyone follows me on this? Okay, kind of makes sense a little bit up until now. Okay, I'll assume hopefully yes. So I noticed this. Okay, so what do I do now? I just rewrite my equation. My equation now is x squared E3x over 3 derivative dx. What did I do? I just replaced this e to the power of 3x. I just replaced it. Nothing more. I just replaced it to this point. Okay. And now is the step that is actually a little bit confusing, which is the step of integration by parts. I applied, so I took the derivative of the second term. Now I got to add the integral when I take derivative of the first term. Okay. So I add x squared. dx, okay, or x squared derivative, or however you want to call it. Okay. I'll just go with this rather. This derivative. Okay. And I multiply by the term untouched. Okay. Notice here, derivative, here, no derivative. X squared, here, no derivative, here, derivative. Okay. And this is equal to x squared multiplied by E3x over 3. No derivative, no derivative. And more importantly, no integral. Okay. So again, I'll write it again because this is like, I'm fairly confident that once you get this, you can take a derivative and see how it goes. But this is important to understand how you phrase it. So I need to solve x squared e 3x over 3. Derivative, dx. In order to do by parts, I need two terms. I have them. This is one term, and this is the other term. Okay, term 1 and term 2. Term 1, term 2. Here I have it taking a derivative of term 2. So I have to add the integral of when I take a derivative of term 1. Okay, so I take a derivative of x squared this time. And I multiply by the other term with no derivative. Okay, I'm just going to rewrite the above thing. And I know that this is equal to no integral and both the terms with no derivatives. Okay, makes sense? Kind of gets a little bit more light on happening something. Okay, cool. And now you just solve it. Why did you do this? Well, now I can take a derivative here. Okay, I know what derivative of x squared is. So let's see what it is. My equation becomes integral of x squared e the 3x over 3 dx. This derivative plus integral. What's this? What's the derivative of x squared with respect to x? This is dx here. It's 2x. 2x multiplied by e 3x over 3 dx. This is equal to x squared multiplied by e 3x over 3. Okay? Cool. Now, yeah, it doesn't look like I made too much progress right now. So just like L'Hopital and basically all the rules that you know, there's no shame in applying it twice. Okay, so I'm going to apply it to this thing again. And this is, I don't know if this is actually one of your assignments for the seminar, but probably it has to be something close about this. Okay. Let's agree on something. You can't actually do on any other term. So this is what I want to find out. This is what I need to compute. And this is done. This is done. So I just need to solve this. Okay. Cool. So let's just solve that thing now. I need to solve integral of 2x e the 3x over 3 dx. This is what I need to solve again. And I said there's no shame in applying it twice, 3 times, or how many times you need to apply it. That's why it's so good on polynomial. Okay, now exactly the same logic. Here I can just take 2 and 3 outside, okay, because it's constant. Remember, constants jump in front of the thing. So this is just equal to 2 over 3 x e 3x dx. Okay. So now, again, let's apply the integration by parts once again. For the last time today, I promise. So e 3x here. I know that when I take a derivative of e 3x over 3, derivative, I get e to the 3x. I know this. So first step, replace in the equation, like replace in the equation. So let's do it. For first step, replace in the equation. Okay, I got to compute x multiplied by e 3x over 3 derivative dx. Good, I replaced. Now, first term, no derivative. Second term, derivative. What do I have to add? Add the other term with the opposite derivative. So I just copy dx and I add the integral where the opposite term is being taken derivative of. So where x is being taken derivative. Okay? Okay. Now, third step, make it all equal to no derivative, no integral. So integral x e 3x over 3 derivative dx plus integral x derivative e 3x over 3 dx. I said make it equal to no derivative, no integral. So the terms with no derivative and no equal and no integral on them. Cool, makes more sense now what I'm doing. Yeah. Yeah, well, I took the 2 over 3 out.
Did you put it back in or not?
Eventually, so I'm here eventually. Remember, I have to compute this thing over here. So eventually I will put everything back in. But right now, I'm trying to help you understand how to apply parts in the first place. But of course, 2 over 3 you compute it at the end.
Okay, so you still have the final answer.
No, we do not. Because I said, so we're here. This is what I need to compute. This is done, but I don't know what this is. I don't know what the antiderivative, the integral, what this integral is. So now I'm computing this integral. That's why I said solve this, need to solve this. So now I am solving this. Okay? I'm just taking it out of the equation so I don't copy everything and it looks cleaner. But what I'm doing is I'm solving that little part from the middle right now. Okay? And it so happens that solving that little piece in the middle, I'm using integration by parts again. Okay? Just to solve that piece in the middle, just to solve this thing. Just to solve this little thing, I have to use integration by parts again. Okay? So this is, and now I'm using this case, this little piece that I needed to solve. And I'm basically showing you the train of thought again of how to use this thing. So again, I find like a derivative because I need derivative in order to apply by parts. So I find it, I replace it in the equation. Replace it, nothing happened up to now. And now I add the other opposite derivative in the sense that here, first term on derivative, second term derivative. Now I add the integral where the first term is derivative and the second term is not. And now I know that this sum has to be equal to the terms with no derivative, no integral. Okay? Cool. And now I can actually solve this. So let's actually solve this. And I know it's a little bit maybe ugly, but I think what you should focus on is the concept of applying by parts. Okay, because that's the most important thing here to follow. How to solve it, how to apply by parts. The other rest of the computation, where it adds and ugly and stuff, that's nothing. Once you understand by parts, that's literally just following the train of logic. No worry about it. Just what is important for you to get after this hour is if I give you like an integral of x multiplied by e to the x dx, can you apply by parts to it? If the answer is yes, then it means you're doing great. If the answer is no, it means I suck at this. But we'll move on. So here, this is the final answer. Okay, I mean more or less the final answer of by parts. This is everything that by parts gives you, and why it's so strong is because I started with this thing. I started with this that I have no idea how to solve. And I have this, which is x derivative is 1. So it's just integral of 1 multiplied by e free x over 3 dx, and is equal to this everything. Okay? And let's look at it now. This is done, as I said. This I want to compute. And this, now after applying by parts 2 times, this now I know. Now I know. Okay? Why? It's just an integral of an exponential, which I know what it is. You have the formula, or if you don't know, you have the formula. I've written the formula here. You have it in the book. I think we started the lecture with it. Okay? So now I know what that is. Okay? I know that this is equal to e to the 3x over 9. Okay, this is it. If you don't believe me, just apply the formula, but it's just integral of exponential, so no one's stressing about it. Now I know this, okay? So I know this, so I can compute this. So my parts was successful because I managed to compute what I needed to compute. Okay? Any questions on this last part? I wouldn't worry. Tomorrow in the hour that we have, we're probably going to do more by parts as well. Because I think that should be enough for you to do the seminar problem. But again, the formula is for by parts. In case you don't like the example, more theory guide, the formula is integral f prime of x gx d of x plus, again, I said, add the other term with the derivative on the other guy. Okay, this thing is equal just to f of x g of x. This is all that we're doing, or we've been doing right now. We've just been applying this thing over and over and over and over again. Because realistically, that's how we're going to solve most of the integrals in this course. Okay? Again, one more time. You have this integral, which you want to compute. This is what you want to compute. And sometimes, most of the problems, you will need to create this f prime. You need to create this, just like we did, okay? Create this. Example. E to the 3x over 3 is equal to e to the 3x, okay? I just created that derivative there because it wasn't there in my initial integral. So I just created it so I can apply by parts. Okay, so this is what you want, and I created this derivative. Good. Now I add to it the integral of my creation here with no derivative, but I take a derivative of the other guy, and this is equal to just their product. Okay, and there's no intuition necessarily behind it outside of this is the product differentiation rule with an integral. So don't ask me if there's any intuition behind it. It's just a mathematical thingy that allows you to compute stuff. Okay, so just focus on learning to applying by parts, and I guess I'll see you tomorrow. On Zoom later, guys.